Good morning, thanks for coming. I know it was a project to find this room in the end of nowhere, so I'm happy you arrived. And today I want to introduce a new file security approach which is based on the learning dynamic permissions in the organization. Just before we begin, a little bit about myself. I'm the Machine Learning Research Manager at Imperva. I have many years of algorithmic experience. And in the last 5 years, I'm focusing in cybersecurity and AI. So I just want to acknowledge my partners in this patent. One of them is Guy, who just arrived to the room. Hi, Guy. He was a data scientist in my team, and unfortunately, he left us to complete his PhD. And the other one is Amichai Schulman, who is one of the 3 co-founders of Imperva and was the previous CTO. So I will start by explaining why the traditional file access control mechanism has failed. Then I will present our approach, which is based on detecting suspicious file access by learning dynamic peer groups. And then I will give an example of our algorithm based on a real environment. So why the traditional file access control mechanism has failed? Today we live in the data era. Organizations have a lot of data and they need to access this data in order to perform their day-to-day chores. This is the reason that the organization gives their employees permissions to access the data. However, many times we see that legitimate permissions are being abused. From our research, we learned that permissions are being abused by malicious insiders. These are employees from within the organization who maliciously steal the organization data. Sometimes we see that legitimate permissions are being abused by careless insiders. These are employees from within the organization who unintentionally expose the organization data to attacks, for example, by copying large amount of data from the IT control to their personal devices. Sometimes we see permissions being abused by compromised insiders. These are attackers from outside the organization who successfully compromised an account from the organization, and from that point they can act as if they were insiders. And indeed, despite the use of access control mechanism, we see that large-scale data breaches occur all the time in the last years. I'm sure many of you heard or even saw the movie of Edward Snowden. Edward Snowden was a former system administrator and contractor of NSA, the National Security Agency of the United States. He succeeded to steal 4 terabytes of data from the organization, including 1.7 million classified documents. So now we understand that we have a problem. But before trying to analyze why the traditional file access control mechanism has failed, let's just remind ourselves how does it work. So we have this matrix of users and folders in the organization. Each user gets permission to access specific folders from the file servers in the organization. Many times these permissions are granted according to the user role or the department of the user. These matrices are very big and it's very hard to manage them. We have many users in the organization, we have many folders in the organization, and many times these permissions should be changed due to change of a position or change of a project, etc. These matrices are very hard to maintain. And indeed, we see that in reality, permissions are granted and rarely revoked. We can look at the graph in this slide and see the average number of folders accessed as the function of the number of years the user worked in the organization. I think it's very easy to see that there is a very strong correlation between the number of years the user worked in the organization and the number of folders he or she is permitted to access. If we look closely, we can see that if we compare the number of folders that are allowed to access after 5 years that someone works in the organization as opposed to the number of folders that are allowed to access in the first year of working in the organization, we can see that the folder permissions are almost doubled. But when you think about it, it's not really supposed to be like that. When I work more years in the organization, maybe I need to access different folders, but definitely not twice as much of the folders I access in the first year I work in the organization. The reason for that phenomenon is the fact that permissions are granted on a need-to-know basis, however many times that they are not revoked. Another interesting phenomenon we discovered in our research is the fact that 75% of the users access less than 35 folders per month. I can even tell you more that 50% of the users access less than 10 folders each month. So in reality, we see that most of the users use less than 0.1% of their folders that they are permitted to access. So we have this permission model, which is far from being a tight model. Another interesting phenomenon we learned during our research is the fact that we can divide the folders in the organization to two categories. The first category are folders of continual interest. These are folders that we see user access to them from time to time and constantly. The second category of folders are folders of temporary interest. These are folders that they are created and then they are accessed for a day, for 2 days, for a week, even for a month. But after they are just forgotten and vanished in the file servers of the organization. I think it's obvious that the second category of folders don't need static permissions model. They need dynamic permissions only for the time of their temporary interest. So maybe you can guess what's the portion between the first and second types of folders? 75, any other guesses? No, so it's very interesting to discover that more than 91% of the folders in the organization are from the temporary interest type. Another fact is that today we all live in an agile environment. We have many projects in the organization who are multidisciplinary. We see that on specific folder we will have users from different departments in the organization that will work on them. We can see a different project that other users from different departments work on, and the same for the third project. So the fact that the traditional file access control mechanism is granted due to the user role or the department of the user doesn't suit today's agile world. So hopefully by now I've started to convince you that the traditional file access control mechanism has failed. Let's just summarize the reason. We see that it's very difficult to maintain. This huge user to folder matrix is a very big and dynamic matrix, and indeed we see that permissions are granted and rarely revoked. We also see that the permission model is not a tight model. Users don't use most of the permissions they are granted. We see that most files are of temporary interest, thus we need to build some dynamic permission model for them and not use a static permissions model. And due to the fact that we live in an agile environment, we need permissions to be granted on a project-based and not using the user role or the department of the user. So now that we understood that the traditional file access control mechanism has failed, I want to introduce our new approach for file security, which is based on detecting suspicious file access by building dynamic peer groups and dynamic permission model. So after we understood the drawbacks of the traditional file access control mechanism, we understood that we need our new file security approach to be agile, to be dynamic, to be flexible, and to suit today's world, and also to be maintainable. So in order to do so, we use a machine learning algorithm. Our algorithm is automatic and doesn't require manual human maintenance. It is also dynamic and changes over time based on the access control to the file servers in the organization. So we learn the normal activity in the file servers of the organization, and using this normal activity, we detect suspicious file access. Due to the fact that many of us are data scientists, we know that machine learning by itself is not enough. In order to successfully and accurately apply machine learning algorithm on data, we need to use domain knowledge. In our case is how users access files in the file servers of the organization, how organization work with file servers, etc. So let's start with understanding how our algorithm works. So the input data to our algorithm is access logs to the file servers in the organization. Specifically, we are looking at which user accessed which folder and in what time. And now let's look at a very high-level view of our algorithm. The first step in our algorithm is learning the peer groups in the organization. This is based on the folder access patterns. And what do I mean by peer groups? Let's look at the example from before. We can look at the blue users who work on project 1. All these users probably need to access specific folders that relate to project 1. This is the reason that our algorithm will learn them in the same peer group. The same we can say about the orange users who work on project 2. They will be in a different peer group due to the fact that they access folders that relate to project 2. And again, the same with the green users of the third green project. So now we have peer groups who are based on the access patterns to the file server in the organization. The next step in our algorithm is to associate files and folders to each peer group that are allowed to access by the user in this peer group. So again, if we're looking on peer group 1, which contains the user of the blue project, this user will be allowed to access folders that relate to the blue project. Same for the orange peer group, that will be allowed to access folders that relate to the orange peer group, and same for the green peer groups. So now we have the peer groups in the organization. For each peer group, we have the folders that are entitled to access by the users of this peer group. Now we can detect suspicious file activity in the organization. We will detect suspicious file activity when we will see a user that accesses a folder that is not associated by his or her peer group, but is associated by other peer groups. So algorithm is a combine of two parts. The first part is the learning part. We call it the profiling part. And the second one is the detection. The goal of the learning part is to learn the normal behavior in the organization. Specifically, the profiler or the learning part learns the dynamic peer groups and the files that are associated to each peer group. In order to do so, the profiler gets 2 months of data, and it is updated daily by new data that accesses the algorithm. The detector uses new data that is accessed the algorithm with the profiling output, which is the dynamic peer groups and the files that are associated to each peer group, in order to detect suspicious file access in the file servers of the organization. So now let's going deeper and understand how the learning or how the profiler works in order to learn the peer groups in the organization. So learning the peer group in the organization combines 3 building blocks. The first one is cleaning the data. The second one is dimensionality reduction. And the third one is cluster users to the different peer groups. And now I will explain each of these building blocks. So the first step is cleaning the data. We know that any machine learning algorithm is as good as the data that is fed to it. And here we need to clean several events in the data that don't help us learning the peer groups in the organization. Sometimes they even disturb us. So we clean folders who are rarely used. An example of such folder could be my personal folder, which I'm the only one who accesses. So in this case, I don't need, it will not contribute the correlation between users in the organization. We also clean popular folders. An example of such a folder could be the 3 pictures of my organization. Obviously, many of the users in the organization will access this folder regardless to the projects that they work on, and it doesn't give us any information about the different peer groups. Many times it will just do the opposite. We also clean automatically used files. These are files that are accessed by processes from my computer, but not by myself. In the users department, we clean users that don't contribute to our peer group because they don't have enough information. For example, a user that works only 1 or 2 days in the profiling window. We also clean super users. Super users are users that, due to their job, need to access many folders in the organization or need to scan all the folders in the organization. An example could be a system administrator who somehow works on maintaining the folders or doing backups or stuff like that. Obviously, super user will not help us learning the different peer groups in the organization. So after we clean the data, we build a sparse matrix. The matrix is users to folders, where entry ij in the matrix is the number of days in the profiling window that user I accessed folder j. Obviously, this is a very sparse matrix due to the fact that we have thousands or even more folders in the organization. However, each user during 2 months of activity accesses only tens of folders or even less. So the next step in our algorithm is dimensionality reduction. We know that some folders contribute more than other folders to learn the peer groups dynamically. We know that some folders are accessed together, so we don't need all the folders in the data. We can use one trend instead of all these folders. So the idea in this dimensionality reduction step is leaving strong trends in the data while cleaning noise. In order to do dimensionality reduction, we used PCA. And after the PCA process, we're left with features for each user. The features for each user are linear combinations of the folders that the user accessed. So now we clean the data, we reduce the dimensionality of the data, and finally we are ready for the clustering of the users to different peer groups. At this point, we ask ourselves which clustering algorithm to use. So K-means is a very popular clustering algorithm, but we understood that it doesn't suit our problem from several reasons. The first of them is the fact that we don't know K. K obviously differentiates between different data sets, between different organizations. Also, due to the way K-means is designed, it requires centroids for each cluster, and many times it doesn't suit the peer groups in organizations. So we used optics, which is a density-based clustering algorithm. Density-based clustering identifies dense cluster of points and allowing learning clusters of different shapes and densities. Another advantage of a density-based clustering algorithm is the fact that it knows to identify outliers in the data, meaning it can, in our case, it can identify users that do not belong to any peer group. And we can look at the example in the slide and see data that is clustered once by K-means with K equal 2 and once by optics algorithm. I think it's very easy to see that optics algorithm clustered the data correctly and also successfully identified outliers in the data. So now when we have the clustering algorithm, we need to choose our distance function. We chose cosine similarity because it suited our problem the best. So finally, we've learned the peer groups of users according to their access patterns to the folders in the organization. Next, the profiler is associating the folders to the different peer groups in the organization. So first, we return all the folders we cleaned for the clustering part of the algorithm. Next, we would say that a folder belongs to a cluster if a user from that cluster accessed the folder during the profiling window, or if it was accessed by a user from a closed cluster. I will not get into the notion of closed clusters in this presentation. However, closed clusters are just similar clusters with similar activity. Once we have the peer groups and we have for each peer group the folders that the users from this peer group are entitled to access, we can go to the detection part. The way that the detector works is that it would say that an activity is a suspicious activity if a user accesses a folder which is not associated by his or her peer group, but is associated to other peer groups. So now I want to show an example of our algorithm in a real environment. In order to do so, I want to introduce Counterbreach. Counterbreach is a product from the Security Insights next generation product line of Imperva. The goal of Counterbreach is breach prevention. It protects your data, organization's data, from insiders. The way that Counterbreach works is the following. It gets access logs to file servers and to databases in the organization, and without any prior knowledge on the organization, it applies domain knowledge-based machine learning algorithm in order to detect suspicious activity in the organization. Suspicious activity in the organization could be a hacker in action, a real breach that happens in the organization, or a security bad practice that is likely to be exploited by an attacker, by a hacker. So now I want to show you a real screenshot from one of our customers' environments that shows the suspicious file access incident based on our algorithm. So let's see what we see here. We see here a user named Mike, which is an engineering manager who accessed a sensitive finance file in the organization. The reason that Counterbreach and our algorithm detected this incident as a suspicious file activity is because typically this file is accessed by a group of users, all from the finance team. So we see that using the access logs to the file server in that organization, our algorithm successfully detected suspicious file access of an engineering manager who accessed sensitive finance file. So to summarize, I've talked about why the traditional access control mechanism has failed. We've talked about the fact that file permission models in today's world should be dynamic. I've presented our new file security approach, which is based on learning dynamic peer groups and dynamic file permission model by using the folder access patterns of users in the organization. And I've talked about the fact that machine learning is not magic, and in order to successfully apply machine learning algorithm, we need to combine domain knowledge with the machine learning. So thank you for listening and for finding this room. I know it was an adventure. Questions? The question that this guy asked is, we have a problem in cybersecurity with the fact that we don't have, most of the times we don't have real examples of attackers who access the organization and do breach. We do have a lot of data, or sometimes we do have data to work with. However, it doesn't represent attackers in many cases. So the way we work with this issue is the fact that we are using the positive model instead of the negative model, meaning we learn the normal behavior of the organization on one side, and on the other side, we try to think of attack patterns. For example, here in this work, we assume that employees would access folders that they should access. And they should access always. And when we see an employee that accesses a folder that is not accessed normally on a day-to-day basis, we would assume that it might indicate a hack.
Hi. My question may be trivial, but I'll give it a shot. Let's say the algorithm worked, and now all users in the organization are clustered into groups. And now a new user comes into the organization. What happens then? Is he initially classified into one of these groups, or you let the algorithm do its work again on this specific user, and I don't know, each folder of file access raises an incident? I mean, what happens then?
So one of our goals is to minimize false positives, and indeed new users is a challenge. So as I told you, the profiling and the detection works on a daily basis. So if I have a new user who accesses the organization, in the first couple of days, it will not be part of any peer group, and thus it will not, an incident will not created on this user. After a couple of days, when we will have enough information on the new user, he will be part of one of the peer groups, and then we will start detecting incidents. You can ask, and it will be a very valid question, so what happens if this user on the first day we see it is an attacker? So we have other algorithms in Counterbreach that address this specific problem.
I'm not sure I understood completely about the file system management. So we have folders and we have people and we want to manage who can access what.
Exactly.
So you manage this automatically, but then there is a system administrator that want to give folder access to this guy or that group. So they do manual work. So you have both manual work and automatic work. How is this combined?
Okay, so this is a very good question. So our belief is that obvious permissions can still be applied using the traditional file access control mechanism. For example, I'm a researcher. Obviously, I don't need to access a sensitive HR folder. So this can continue to work with the static permission model, but this is just the beginning. On that, due to the fact that we see that legitimate permissions are being abused by insiders from many different types, we built our approach, which is dynamic and which makes the permission model much tighter and dynamic.
But eventually your model gives just regular permissions, just like it is today in the file system?
So it doesn't really give permissions. The way it works, it detects suspicious file activity. Someone should go over these incidents and see if indeed this is a suspicious file activity, and in that case, work accordingly. So you can ask me another valid question, but wait, if I have an attacker in my organization, he will succeed to access the first suspicious folder, and probably after a couple of hours or after a day, you will detect him. And in this point, I just want to tell you about the statistic of data breaches done by insiders. The statistics are that it takes months or even years to detect suspicious activity done by attackers in the organization. So the fact that I will detect suspicious file activity after a couple of hours or a day is a very, very good improvement of the situation we have today. Thank you for that.